There aren't really very many options. All right, so this is the cyanide ion here, Cn minus, a diatomic ion. When you look at this, carbon has 4 electrons, plus nitrogen has 5 electrons, and there's a negative charge, so that's 1. That's a total of 10 electrons. Okay? So we have a carbon, we have a nitrogen, there's no center atom in a diatomic. So we'll take the next step and we'll put in our starting point of single bond. Put in a single bond, take away 2 electrons for the single bond. That gives us 8 electrons to put on the atoms. And a reasonable way to do it is to put 4 on the nitrogen and 4 on the carbon as a good starting point. And now neither one of these atoms has an octet. So we have to do the usual trick, and that is step 5, take a lone pair from one of the atoms and make a multiple bond with it. So let's suppose we take that lone pair and make a carbon-nitrogen double bond. Keep in mind this is an anion. So carbon, now 2 bonds to nitrogen, and that leaves the nitrogen with 1 lone pair and its interest in this double bond. So the nitrogen still doesn't have an octet. Carbon's looking good, it's got an octet, but in order to get nitrogen an octet, we have to do step 5 again and pull a lone pair off the carbon who has 2, and then build the triple bond. And remember that this is a monoanion. Now, do we have octets on both atoms? We do, don't we? We do. Questions on cyanide ion? I would appreciate it if you didn't use the computer, but used a piece of paper. You'll learn more. Okay. Let's do the next one then. How about the ozone molecule, O3? It's a very active molecule. There are 6 electrons, valence electrons for each oxygen, times 3 oxygens. This is an 18-electron system. And we will put one of the oxygens in the middle. Now, of course, you could draw a triangular structure for this molecule. And somewhere along the line, usually somebody asks about it, but after we get into chapter 11, where we look at bond angles and so forth, we'll see that the triangular structure for O3 is not a viable one. The angles are no good. All right, so we have our 3 oxygens. We'll draw a single bond between each set of them. So that's 4 electrons. And that leaves us 14 electrons. And so we'll start on the outside oxygens and put 6 around each one to make an octet. And so 14 minus 6 is 2 electrons. That leaves a pair of electrons for the oxygen in the middle. And the outside oxygens have octets, but the one in the middle doesn't. And so we have to go step 5 again. And now we hit something new. Okay. Too much talking, please. We hit something new. There are 2 different places we could do this from. If we do it this way and take a lone pair off of this oxygen, these 2 oxygens are equivalent to one another. They have the same number of electrons, and they're both the same type of oxygen. If we do that, let's see what we get. Write it down. That leaves 2 lone pairs on the right-hand oxygen and 1 lone pair on the center oxygen and 3 lone pairs on the left-hand oxygen. Have I satisfied the octets? No? Which one isn't satisfied? They are all satisfied, aren't they? Each oxygen has 8 electrons around it, so this thing is octet. Okay. But there's a problem, and the problem we'll get to in a minute, but this Lewis dot structure suggests that there are 2 different kinds of oxygen-oxygen bonds. A double bond, which would be shorter and stronger, and a single bond would be longer and weaker. But the experimental evidence is otherwise. The experimental evidence says both of the bonds in ozone are equal in length and in strength. So we're going to put a little question mark there and come back to him in a minute.